Everyone, welcome back to 3 Deviations. In this video, we are going to be covering implicit differentiation. So last time we talked about the hyperbolic functions, and we're talking about all the different functions before that, how to differentiate them. Well, implicit differentiation is a little bit different from what we've been doing, and it's going to be a little bit harder. Implicit differentiation is a difficult concept to grasp. It's probably one of the first really challenging concepts we are going to come up on in single variable calculus. And with that said, I think it would be a good idea if you watched my previous videos, if you haven't covered any of the differentiation rules or trig derivatives or logarithmic derivatives, because that's going to be helpful in this video. All right, so let's start off with the concept of implicit differentiation. So let's say I have an ellipse. Let's say I have an ellipse. It's not going to be a very nicely drawn ellipse, of course, but it's going to be an ellipse nonetheless. There's our ellipse. And let's say somebody comes up to me and says, take the derivative of the ellipse here at x equals a. Let's call that a. And I'm going to be left with a problem because I need to find two tangent lines. I need to find a tangent line there, and I need to find a tangent line there. And the problem here is that because this ellipse isn't a function, I'm going to have two tangent lines. Because if you can tell, this didn't pass the vertical line test because I need to take two tangent lines. So this ellipse is not a function, and we need to differentiate it like it's not a function. If we wanted to, we could solve for y, and then we need to take two derivatives, but that's going to be tedious. So that's why we have implicit differentiation. And as I said, it's going to get a little technical, but that's okay because we're going to work through it together. So the technique for implicit differentiation. First, we need to make sure that our function is implicitly defined. I could have a function like y equals x. That's definitely a function. I could literally write that as f of x equals x. So that's definitely explicitly defined, an x squared or x squared plus 1 or anything where I have y isolated, and I can easily see that I have it defined in terms of x. Now if I had something like xy plus x sine of y squared equals y over 2, that's not explicitly defined because I've got this y tied up in the argument of the sine, I've got it multiplied with x, I've got it in this fraction here. It's going to be a pain in the neck to simplify and then differentiate. So instead what we're going to do is we're just going to take the whole equation, we're just going to take this whole big thing, we're going to differentiate it with respect to x. And then when I differentiate y with respect to x, we are going to be left with some dy dx's, but that's okay because we can solve for that algebraically later on. And then we will be left with some sort of relationship between y and x that is going to allow us to find our derivative and plug in some points. So let's try with a circle. Let's say I have the circle x squared plus y squared equals 25. And I want to differentiate this. I want to find the derivative. So what I could do if I did not have a great lecture on implicit differentiation, I would just do this. I'd say, okay, well, we're going to divide the circle into two semicircles, and this is a function, so we're just going to take the derivative of this function, right? And then we're just going to take the derivative of this function. And then we'll have our two derivatives, and that's going to be great. No, it's not. That's going to take you a long time. So what we're going to do instead is we're going to differentiate everything with respect to x. We're going to do implicit differentiation. This 25 is just going to go to 0 because it's a constant, and when we differentiate a constant, it becomes 0. And then we will differentiate x squared plus y squared, and then we will get 2x plus 2y dy dx equals 0. This dy dx comes from the chain rule when we differentiate y with respect to x. And now all that's left is some algebraic simplification. We've got to isolate dy dx. So we are going to subtract 2x, and then we're just going to divide by 2y. And that is going to give us dy dx is equal to negative x over y. So if I wanted to find the derivative at any point on my circle, I'd just plug in the coordinates. If I was given the point xy on the circle, I'd just plug x into here, and I'd just plug in y into there, and then I'd get my slope. So that's how implicit differentiation works. It's really not that bad. But then we can start coming up on some more tricky examples, like this one here, when I have x cubed plus y cubed equals 6xy. But we're going to go through all the same steps. We're going to differentiate everything with respect to x, and we are going to be left with 3x squared plus 3y squared dy dx is equal to 6x dy dx plus 6y. And that is our derivative there. And now again, we're just going to solve for dy dx. We're going to make sure that all of our dy dx terms are on one side and all of our x and y terms are on the other side. And then we are going to factor out a dy dx, and then we are going to divide by y squared minus 2x, and that will give us dy dx is equal to 2y minus x squared over y squared minus 2x. And that is our derivative for our second example. Now we're going to do a slightly more challenging example. We are going to implicitly differentiate sine of x plus y is equal to y squared cosine x. So we've got a little bit of trig in here. Okay, so we are going to differentiate everything with respect to x, and that is going to give us the cosine of x plus y times 1 plus dy dx equals negative y squared sine x plus cosine x dy dx. And as always, we are going to simplify that, and then we're just going to move all of our terms to one side and then move our dy dx terms to the other side. And then we are going to be left with our dy dx is equal to y squared sine x plus cosine x plus y over 2y cosine x minus cosine x plus y. And that is our final example. That's the answer for our final example. So you may have noticed we didn't do very many applications, but good news for you, implicit differentiation has a whole video dedicated to its applications called related rates. That's going to be very helpful to our understanding. And then implicit differentiation still isn't going away because we are going to use it to derive the derivatives of the inverse trig functions. And then after that, we are going to say bye-bye to the methods of differentiation and hello to the applications of differentiation. Thanks for watching through Deviations. Please like and subscribe. We will see you back here next time.